Hi guys, happy Monday. Uh, Interesting times, right? Well, I hope you had a good break or as good as it could get. And we're back. We're back. You know that although this course is online, everything has gone online now, and something has changed for other courses, but not for FIT585. So we're gonna keep doing whatever we said we're gonna do, and there's no reason for us to change anything. The purpose of this video is to talk about what you submitted before the break and talk about what we're covering this week and what you need to submit by the end of this week while listening to some good house music. All right? So, two chapters for today, but before I go there, I want to talk about LO12 and LO13. LO13 is great, I don't have anything to say. LO12, it was talking about how many members of IACUC have to be vets, and that's one out of those five. And you can find that information on page 225. Right? That's all I got. Other than that, pretty good. You keep sending me emails, and I keep replying. It's going pretty well. It's going pretty well. I'm pretty satisfied, and we're gonna cover two more chapters today and move from there. I don't want you to worry about anything. We're gonna be fine. Don't freak out. We're gonna be okay. Okay. All right. Chapter 14: Conducting a study, pilot testing, sampling, and data collection. That's an important chapter. Not very long, but it has a lot of good info. So in the beginning, we need to talk about the sample, right? The study sample. So when we design our study, we have to actually execute it, and one very important part of it is to talk about the study sample, which means which are going to be the characteristics of the people or the animals that will participate, right? That's really important. So we're looking for a representative sample from the whole population. So whatever we find from the sample, we can extrapolate it to a bigger sample or the whole population if possible. So we will talk about inclusion criteria, and that can be age, sex, PA levels, diseases, chronic conditions, anything that will um, make somebody eligible to participate or not. So the size, how many, right? And that's one thing that you have to think about when you are going to propose your study. So we don't need a sample that is too small, because then it's underpowered. We don't have enough data to extrapolate. But at the same time, we can have a sample that has more participants than we actually need, because for many reasons, like it's a loss of resources, it's unethical to put more people through something, or animals, if we don't need to, and so on and so forth. So it can be very problematic, the size of the sample. So in order to solve that problem, we do usually power analysis. So a power analysis will give us the appropriate sample size. Usually we add a little bit just because of attrition. Maybe we'll lose some here and there. So that's based on the expected outcomes, which are based on a pilot study. We'll talk about pilot study in a little bit, or what other people have done before, like what's out there in the literature. And there is software that can help us with that, right? Recently, we submitted a paper. We used GPower, and there you can put several pieces of information like the alpha level, and you have a question about that in your LO. You have, usually we put it at 0.5, P is at 0.8. So you can put some specific directions in the calculation, and then you get the sample size that can give you whatever you're looking for based on the alpha level, the power, and so on and so forth. Now, when we're doing the sampling, we have to take into consideration the inclusion and exclusion criteria, also the ways we can or we will recruit participants, and also we should never forget that randomization decreases bias. All right. Now we have two major ways of doing it: probability sampling and non-probability sampling. Probability sampling can be broken down into three subcategories: simple random sampling, so everybody has the same chance to be recruited, and me being recruited doesn't affect your chance to be recruited. Systemic or systematic in some other books, sampling approach. Uh, we have a predetermined manner of doing it, like 1 out of every 3, right? People that we see, something like that. And stratified random sampling, we within the sample we have specific subcategories. This group will be all tennis players. This group will be all divers. Right? Now, non-probability sampling is very popular in XFIS. It's very popular in XFIS because we want participants to actually volunteer to participate. So there's no equal probability of all participants to be selected. Is that good? Is that bad? Well, it depends. The thing is here that whether we're talking about probability sampling or non-probability sampling, the assignment, the random assignment, has to take place anyway. All right, do not forget that. Pilot testing. What's pilot testing? Before we actually do the study, we can do a smaller study or a part of the study, depending on how it is designed to check quality, feasibility, time, protocol, readiness of equipment or personnel. Will help us design applicability. We'll check validity, reliability of tools. Can practice data entry. We can practice data analysis, and we can reevaluate after the whole process with a very specific goal. We're trying to decrease the time of doing it and the cost, and increase the quality and the feasibility of the actual study. Right? A lot of times we do pilot studies to see. We have a hypothesis. We're trying to see if it's actually going that way, and then we make it bigger. We do a pilot study, and then we have enough preliminary data to ask for funding. Right? There are many ways you can do it. In general, it can increase the quality and the feasibility of a project, right? Or you can abandon it overall if you think it didn't really go the way you thought it would. Figure 14.1 will give you more information about that. Data collection. When we're doing data collection, timetable is important. We need to understand when, because you don't want to. Data collection can take a lot of time depending on the design. So you need to have specific goals, right, and times. Consent form, of course, before data collection. There are a lot of external factors that we have to take into consideration. I have a lot of friends that everything was great, but data collection just didn't go as planned because of the external factors, which can be really a very specific target group that were your participants you were trying to draw from, right? Dietary intake may need to be controlled. And in general, you need to have some stability, constant methods on the way you collect data, right? So for this chapter, pretty short, not very important, right? Let's make sure we know the glossary and we understand how we figure out sample size, sampling, and of course, how and why we do pilot testing. All right. Now, chapter 15. And before I go to chapter 15, it's a little bit technical. I don't want all that kind of information, but I want you to understand at least how we collect data, how we quantify it, and why we calibrate some the tools that we're using, right? Before I even go to chapter 15, I want everybody to understand that for next time, not only we'll have two LOs, LO 14 and LO 15, Also, as you can see, we have uh, social behavior research investigator and key personnel basic course. That's a course that that's the most basic when you do research, right? And I do all my arrays, take it when they help me in the lab. So I want to prepare you. Some of you that you have already done research, you already have it, which is fine. You just send me the certification. For the ones that don't, you click on it, this one, right? You go to the city program link, you create an account, you don't pay anything. Everything has to go through your affiliation with SUNY Plattsburgh, right? And then you pass that specific training, you do the material, you pass the specific training, and you send me the certification of completion. You submit it on Moodle, and that's it, right? You get your points. I just wanted to say that as a break in between the two chapters. All right, chapter 15, longer chapter, way more technical. Again, I don't want you to know that. I'll stick to the important things. So when we're measuring, when we're doing research, we're trying to measure phenomena, right? Why are we measuring? Because we need to quantify. For example, we'll get some numerical values of whatever. So first we observe, and then we're trying to measure what we observe. Now, we need to make sure that there's validity in our measurement, right? Which is, as the book says, the degree of success in describing, quantifying what is designed to measure. And that's, of course, very important. Usually, we are comparing our measurement tool to a gold standard. And if it's very, very close, then that's high validity. Reliability. Again, from our book, the degree to which a measurement technique can produce consistent results each time it is used. And then, although we talked about that before, we have the intra-class correlation coefficient, which is a modification of the Pearson correlation that most people know, are usually, right? And it has to do with measuring reproducibility. Coefficient of variation is the standard deviation of the measurements expressed as a percentage of the mean. And then we have technical error measurement. So we're measuring the same phenomenon multiple times, and there's some variability which we're trying to minimize, right? Another term, minimal detectable change, the smallest amount of change beyond technical error measurement. That is a true change between two time points. Minimal worthwhile effect, the smallest change in the measure. Standard measures that we have, usually as you will see in our book, we use international system, and the acronym is SI, Système International in French. So we have meters, kilos, and seconds, most common ones. Now, when we talk about the components of a measurement system, from analog we're moving to digital. Okay, technology has helped with that, and we can do that through sensors, amplifiers, AD converters, and computer and software systems that we're going to break down in a little bit, but I don't want you to know too much. What's a sensor? So a sensor will help us receive the physical quantity of a phenomenon and convert it to an electrical signal, right? So we have a range of input, that's important in sensors, sensitivity, the change in the output of the sensor for its unit change, resolution, smallest change that can be detected, response, how quickly the sensor produces output, and cross-sensitivity, if the sensor sensitivity can be affected by other phenomena. And I'm going to talk about that. I'm going to use an example that happened to us in our lab. Amplifiers, so we have low voltage signals that we have to amplify them through an AD converter. The conversion is happening so we can have some data in a form that we can actually use it. And for the analog to digital resolution, you just check table 15.1, you'll see a lot of information. Let's keep going with some terms. Sampling rate, how many discrete measurements can be converted and transmitted per second. Okay, that has to do again with AD conversion, and that's characteristics of whatever machine we're using. Sample period, the time between two consecutive samples, wireless or wired. So we have wired, we have Bluetooth. For example, for us, and I submitted a grant for that, it would be great if I had EEG that is wireless. And Mobita is the best one out there because you can move and so on and so forth. While wearing it, but it costs anywhere from 14 to 18,000 per unit. So wireless is great, but it's usually more expensive. Gives more freedom for most of the time, and we're trying to go wireless, obviously, in our research. Calibration, that's another thing. Measuring known quantities and recording them uh, from the AD converter to see if they're actually close, right? And then it's better to have multiple calibration points than actual two. Two important terms here, the zero offset and span. Span has to do with the slope of the output line, and the zero effect is the y-intercept, is the reference point. And both of them, they create the equation of calibration. And you'll see some examples in the book. What we are trying to avoid here with the zero offset is zero drift. We'll talk about zero drift in error in a little bit. Let's talk about the range over which to calibrate. We can calibrate over the full range of whatever tool we're using or the one that is necessary for us. When do we have to recalibrate? Whenever we are unpacking something, whenever we're moving it, whenever we change a part, after a specific number of use, or after a specific period of time. For example, we have a bike here, right, that we're using for VO2 max testing. So when we took it, we had to calibrate it, so 0 is 0, right? And after a specific number of use, according to the manual, we have to recalibrate it because we need to know if we're measuring what we're supposed to measure. And we don't want that zero drift, right? We think it's 0, but it's -1 or +1. So that's important. So we have bench calibration, that's what we did here, right? Because we did in the lab, but we also you can have field calibration that you do when you do research in the field. All right. I hope this chapter is a little bit dry. I'll admit it. But as you do research, this will make more sense to you. I promise. Sources of error. Okay, error is not good. So our goal is to minimize error. We can avoid it, but we try to minimize it. So we have span error when the slope is incorrect, and then we have a scaling factor to fix that. Have the zero error, that we have the zero offset, and then we add or subtract. So let's say we have scale, right? In 0, we think it says 0, but it's 5 pounds. And then it's 0 drift. So there, if it's 5 pounds and we think it's 0, what we're supposed to do? Whatever we got at the end from all the participants, take out 5, right? Hope that makes sense. Combined span and 0 is, again, it's fixable, but it's more complicated because it has to do with the slope and the intercept. And always have a calibration log just so you remember when you calibrated last time, what was the issue, if you see an issue in a specific machine like a pattern, and so on and so forth. Systematic error. We have the span error, systematic error, zero offset is systematic error. Systematic error is easier to fix because it's everywhere compared to random error, which is harder because it's random, right? So if, for example, we do EEG, right, we were measuring again in our lab brain waves, and one day there was some drilling in the building, or we forgot to tell all the RAs to take their cell phones out of the room, right? That one day, or that one participant, and then our numbers are off. What can we do? That's a random error that we cannot really just subtract or do anything with it. You understand that? So it's harder when it's random. Digital filtering. So it's crucial because it shows you has to do with the type of filter and the cutoff frequency. It happens, like for us with EG, we do it all the time. So you may have a high pass filter, everything below that is not recorded. A low pass filter, anything above that is not recorded, or is removed, let me put it that way. So you clean, there's a way to filter whatever you measure so it makes more sense, okay? Not filter to remove something very specific like the sound of my breathing. We know that is consistent, so we take that out because it interferes with something else. And then we have the Nyquist sampling theorem. I don't want to be very specific about that. Nyquist sampling theorem, it was very important even for the music industry, right? that created the CDs, compact disc. But let's say it says pretty much that, let's say, the human ear can detect sounds up to 20 kilohertz. That we should record a frequency up to 40 double kilohertz, because that will allow us to catch all the possible detail. That's very simplified. That's all I want you to remember from that. And as we're going towards the end of this chapter, we have the data processing, we have differentiation, integration, the area under the curve, and normalization. You don't really have to know a lot about that. And the last thing is reporting. We have to report how we measure things. We have to report how we calibrate the machines. We have to report how we process data, right? All this has to be reported. That's really, really important, at least. Now, for this chapter, glossary, validity, reliability, how we're trying to minimize error, the components of a measuring system, and how we're doing not so much the processing, but definitely that we need to do the reporting part. That's all from me. To the lows and the training for this week. I hope you're safe. I hope you're doing well. Do not freak out. I'm here as a coordinator of the program. The undergrad, the coordinator of the grad program is here. The chair is here. We're all doing our best, during these difficult times. So we'll be fine. We'll be fine. I'm here to reassure you that we'll be fine. And before I finish this video, as always, lift intentionally, not habitually, even if you have to do it this time inside your house. Bye guys, have a great week.